All right, let's look at question 5. This is from section 3.1. So again, we have a function g, and we're told some data about it. So we know that at x equals 2, we have a critical point. And we know some things about the derivative around this point. So let's do this. Let's make a sign chart for this derivative. Sign chart's going to be, really, we only know things about this function from 1 to 3. So we know that f prime of 2 is 0. We also know that, sorry, not f, g. We also know that the derivative leading up to x equals 2 is positive, and the derivative following x equals 2 is positive. So basically, this function is increasing everywhere on this interval except for a single point. So what does that mean about what my function looks like at x equals 2? So let's draw a portion of a graph. So at x equals 2, let's say that my function passes to this point here. At this point, I have a horizontal tangent. So my graph is going to flatten out there. But I also know that from 1 to 3, my function is increasing, and then it reaches, the derivative becomes 0, and then after this point, the derivative goes, or the function goes back to increase. So because of that, I think I neither have a local min or a local max at that point. So hopefully the sign chart and the graph I made from that are convincing. Basically, you can, if you have a local maximum, then your sign chart needs to go from positive to 0 to negative. If you have a local minimum, your sign chart for the first derivative has to go from negative to 0 to positive. We have neither of those things. For part B, suppose that g double prime exists for every x on this interval. Describe the behavior of g double prime of x for values of x near 2. So probably makes more sense to do this since we've already done some drawing. All right, so suppose that g double prime exists for every x. All right, so what's the concavity look like here? So if we believe our graph is correct, and hopefully you're convinced that it is, then what does our concavity look like from x equals 1 to x equals 2? It looks like in this area, I have a function that's concave down. And on the second half of the interval from 2 to 3, I have a function that's concave up. So now let's draw a second sign chart for the second derivative. So g double prime. So I'm only looking from 1 to 3. It looks like from 1 to 2, I have a function that is concave down, so negative. And from 2 to 3, I have a function that's concave up, which means there must be a point, and it's going to be right at x equals 2, where the concavity is, or where g double prime is 0. So I have an inflection point. So reasoning graphically, yeah, I think I've done that. So if I were to describe the behavior of g prime for x values near 2, yeah, as I progress from left to right around x equals 2, my function goes from concave down to an inflection point to concave up. And finally, C, besides being a critical number of g, what is special about the value of x? And okay, so we sort of incidentally answered this question as we were going through this. Since the concavity changes direction at x equals 2, we can also, so not only is x equals 2 a critical point because the first derivative is 0, it is also an inflection point because the graph goes from concave down to concave up, or equivalently, the second derivative goes from negative to positive.